Phenol is a lovely compound that you used to encounter an awful lot more in everyday life, but of course, along with many other very useful chemicals, it has been classified as being nasty, dangerous, and so forth. Anyway, phenol is just a benzene ring with an OH attached to it. Some people would call this an aromatic alcohol. I would suggest you desist from doing that, because while it does have a couple of reactions in common with alcohols, most of its chemistry is very non-alcohol-like. I almost said non-alcoholic, but that of course would have completely different connotations. First thing is that phenol is acidic. Its Ka is 1.6 times 10 to the minus 10, which means a solution of phenol, depending on the concentration, has a pH about 5. Now, of course, if you've come here almost straight from an acid-base module, you think, nothing with that, it's not very acidic. But it is acidic. And if you compare that to, say, ethanol, the Ka of ethanol, 1.6 times 10 to the minus 16, ethanol is much more likely to be a very, 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 very weak base than it is an acid. Phenol is an honest, definitive acid. Now, going to look at the acidity of phenol just very, very briefly, because after all, this is not an acidity chapter. But if you take phenol and you react it with a strong base, for example, sodium hydroxide, well, phenol is an acid. That means it's a proton donor. So it will donate that proton to the base, leaving behind its conjugate base, the phenoxide anion. Okay, now this phenoxide anion, it's an O- attached to a benzene ring. O-, you have a minus in what's going to be probably a p-ish type orbital, and in an aromatic you have all those pi electrons in a nice little circle. And what makes phenol a good acid is because its conjugate base, this phenoxide anion, is stabilized by interaction of that negative charge with the electrons in the pi cloud. Now, some A level, that's as far as it gets. But I do want to take this opportunity just to show you resonance, the sharing of electrons, the sharing of charge, in this case, around an aromatic ring. So I'll start off with my nice little phenoxide, but now I made it obvious that oxygen, of course, has lone pairs. Well, the two electrons from that lone pair, now I must point out everything I'm drawing here is our attempts to model what's going on at this molecular level, okay? But one way that we express extra stability is we demonstrate in our models how we can spread charge around a ring. So it's not just localized on, in this case, the oxygen atom. So two electrons from the oxygen go in to making an extra bond to this carbon. Now at that point, this carbon says, well, that will give me 5 bonds. I can't have 5 bonds. So why don't you, carbon over here, take something with those electrons? So this carbon says, well, if I'm removing that bond, then I'm kind of grossly electron deficient. So I'm just going to take those electrons to myself. And so you make this resonance structure, okay, indicated with this double-headed arrow here, that these structures don't really exist in the same way that this structure doesn't really exist. It's a way for us to model how the electrons, these extra electrons in the phenoxide anion, can be spread all the way around the ring. So now we've got a structure in which we've got the negative charge, the extra electrons on the oxygen, but also one in which it's shared here within the aromatic ring. And we're not finished yet, because now this carbon can say, you know what, I don't really want all those electrons. I'm going to use them to make an extra bond to this carbon here. And this carbon here says, well, I'll make that bond with you, but that means I've got to break this bond with this carbon. And this carbon here says, well, why don't I just take those electrons to myself? Thus giving us this resonance structure. Again, doesn't exist, but now we have modeled how we're spreading out this extra electron over 3 different positions. And of course, I'm sure you can see what's going to happen now. This carbon says, well, those extra electrons were nice, but why don't I share them with you? And if I share them with this one, then this one says, don't want this double bond here. So these electrons in that double bond, the pi electrons in this double bond, will become localized on this carbon. Electrons like that, giving us a 4th resonance structure. And then we can actually complete the cycle, because if these two electrons go to a bond here, and then the extra pi electrons go back into a lone pair on the oxygen. So phenoxide is a very stabilized anion, because that extra negative charge can be delocalized around the entire aromatic ring as well as the oxygen. And because phenoxide is a very nice stable anion, phenol is an acid, because phenol can donate the proton to make that nice stable conjugate base phenoxide anion. So I said at the start of this that phenol is not really an alcohol, even though it looks like it's an alcohol stuck on a benzene ring. And I pointed out in the last slide that phenol is very, very acidic compared to an alcohol. Well, the other thing that phenol is, it's very reactive on a benzene ring, because it activates the benzene ring towards electrophilic aromatic substitution. Now, I talked about activating and deactivating the benzene ring in the extension material for the aromatics module, and I direct you there for more details, especially seeing how it is that phenol activates the benzene ring. But the important thing is having that OH there makes benzene ring much more active. For example, if we take phenol and we boil it up with dilute nitric acid, we will make 2 nitrophenol and 4 nitrophenol. Now you should compare that to how did we stick nitro groups on a benzene ring. We needed concentrated nitric acid and sulfuric acid to activate it, not just a nice friendly little dilute nitric acid solution. Similarly, if we take phenol and we mix it with bromine water, we can make 2,4,6-tribromo-phenol. Okay, so we can really easily brominate phenol. Compare that to with old benzene. In order to put bromine atoms, to substitute bromine atoms on a benzene ring, we had to use liquid bromine, pure bromine, not bromine diluted in water, but bromine, pure bromine, with a catalyst. Okay, so phenol, the OH group, is very acidic compared to alcohol groups, and it activates the benzene ring. Thus, most of its reactions are associated with electrophilic aromatic substitution of the benzene ring, not the OH group. I will point out there is no nucleophilic substitution at the OH, as we would see with alcohols, and there's no eliminations, as we would see with alcohols. I mentioned in the notes previously that I could at this point start talking about esters, which is one place where it does behave like an alcohol, but I'm not going to talk about esters until we know more about carboxylic acids. So phenols, I've got it with the alcohols, mainly because there wasn't another really good place to put it, but phenol is not an aromatic alcohol. It is a very reactive, acidic aromatic compound.